Now starting lecture 8.4, number 4 in that series of very intense chemical concepts here. All right, so we left off with just a quick review here. First thing we wanted to do was find the acetate, which is the weak acid after it has given up its hydrogen, and we were able to do that with 0.25 molar. And then now, of the rest of that, we have to kind of figure out what is the Kb value for this reaction, which is that it, in theory, could react with water to pick the hydrogen back up and then make a very, usually a small amount of OH, but definitely something that can be calculated here. All right, so we know what Kw is, and the Ka was provided for us. So that gives us the amount of, the equilibrium constant, which you can see is a really, really small number. So let's go right from the number that we just calculated in, I believe it was step 1. 0.25 molar is the acetate. The water, you don't need that, and it's not going to have any effect on the reaction. You can't talk about a concentration of pure water. So these are both 0 at the beginning, and then you got your minus x plus x, and of course the equilibrium concentrations. This is going to look and feel very familiar to you. Xx is a real small number, as you remember, to the minus 10th, so we can ignore that one and simply say that x, or the concentration of these guys, is equal to the square root of 0.25 times the Kb, which ends up being a concentration of 1.2 times 10 to the minus 5th molar, and not really concerned about that one. We're very concerned about that one to see what the pOH is, and we can get that. You can guess it's going to be somewhere in the neighborhood of 5, and so we'll start with pOH equals the negative log of 1.2 times 10 to the minus 5th, and that's 4.92, or the sig fig's right, you betcha. 2 there, 2 to the right. And then to figure out the pH, of course, they got to add up to be 14, and you get 9.08. It's slightly basic due to the presence of the basic anion CH3COO, which is an acetate. Okay, so and there is the proof of that, the 9.08 pH, slightly basic. All right, so that was weak acid with a strong base. Now, what about a strong acid with a weak base? Weak bases will accept protons. They don't necessarily want them. So what they are is they're like, okay, yeah, I could take a proton, but I don't really want them. And then you got this pushy strong acid going, take that salt shaker. All right, okay, well thank you. Okay, so the acid is going to force itself on the poor little weak bases and ask them, to take that acid. So we want to first start with how do we write the chemical reaction for this. So we have 2 molar NH3 and 2 molar HI. They're both mixed. How do we write the chemical reaction for what's going on here? Well, in this case, the spectator ion, can you look at that and figure that out? Yeah, it's going to be the iodine is just not going to be involved here. So it's the NH3. You could write it as H plus. It would be perfectly acceptable. But in this case, we want to use the H3O plus so we can see, the two products, and which of course would be ammonium and water. All right, and it wouldn't change anything when you were writing the equilibrium law expressions, except for you'd have H plus instead of H3O plus. So, This question you're going to be much better at. We won't have to dwell on this one as much. The two aqueous species that have the highest concentration, well, this is sort of a one-way arrow here. So it's going to be this one, and that's a aqueous ion. And then, of course, it'll be the iodine from the iodine minus. Okay? So it's kind of using the same philosophy we did with the acids and bases. Okay, now this one is a little more involved, chemical reaction. So if you had equal volumes of potassium carbonate, and which is 0.1 molar, and 0.2 molar hydrobromic acids are mixed, to write the equation for that one. So obviously the potassium's kind of out of play there. So you just put the carbonate plus the hydrogen from the hydrobromic acid. So the Br is out of play. And then it makes that H2CO3. Okay? And you remember whenever we're talking about carbonic acid, that will immediately decompose into CO2 and H2O. Giving your final reaction, the carbonate will react with 2 moles of hydronium ion to give you carbon dioxide and H2O. I'm having a little carbonic acid right here, a little Buble, sparkling cherry Buble right here. You just taste those CO2 bubbles in there. Delicious. All right. So carbonic acid is going to do that. And you see these lots of one-way arrows on something like that. So that was just a good example of what happens when you see that carbonate as your weak base. It is going to go into CO2 and H2O. Good to review that because that's an important one. So now what do we got going on here? Here is potassium phosphate, 1 molar. They are equal volumes. So 2 molar HBr, and we're going to end up writing the net ionic equation for this one. You're going to be leaving out potassium, and you're going to be leaving out bromide. However, we are going to have to add a couple of acid molecules, as you'll see when you write, because we're just talking about removing the one hydrogen from the phosphoric acid. It always would have that one thing right here. So when you add the two of them, it's kind of the reverse of that process. Okay, so you'll be adding 2, so it just has the one hydrogen removed, if you think about this in the reverse. And then you've got the 2 water molecules neutralizing the H3O+. So that will happen, and of course you needed the 1 to 2 molar concentration to achieve that. That's how you know that it is going to do this thing. And this process, remember when we talked about polyprotic acids, of ripping off, the one hydrogen from it. That's what you get as a product there. So that's why you had the negative charge, and of course charges are nicely balanced with the 3 minuses and the 2 plus charges there. Okay, so now identify the aqueous species that have the highest concentration. Well, this one's going to be in the running because it's a one-way arrow, and you also have some potassium and some bromide. And for this one, notice what they did here. They said potassium's going to be in first place because there's the molar concentration would be like 3. And in second place, the bromine would be 2 moles because of the 2 molar right there. And then this would be in third place because of the 1 to 1 to 1 molar. So you could rank those. This would make a really good multiple choice question for a reaction like this. Okay, now here we go. Strong acid, weak base. Let's crunch some numbers. You got the 2 different volumes and the 2 different concentrations. Hopefully you can almost do that in your sleep of knowing that that's going to be turning into moles. You're going to need the balanced chemical equation to figure out the limiting reactant. So that's what we got to do first here, where the NH3 is sort of force-fed these hydrogen ions right there. So that's a relatively simple 1 to 1 to 1 to 1 molar ratio. You're going to do the moles, and I'm going to go through this relatively quickly because we have been down this road before. This is a liter to mole conversion using the same thing that we've done. We got our mole to mole using the balanced chemical equation. So you can see that the NH3 is going to be your limiting reactant. And for a strong acid, when the strong acid is the reactant, the pH can be found from the excess moles of that. So that makes this a pretty straightforward problem because you just figure out the moles of each. Again, they were 1 to 1 molar concentrations, but I think it's a good idea to show where these moles came from. You can't really turn moles of NH4 into moles of something else you're looking for. So you got to kind of say, well, I'm going to start with the H3O plus over here, and I got 0.31 moles of that. I start with the NH3 right there, and I get 0.25 moles, and then you just subtract them, and you can show your work there. 2 places to the right, 2 places to the right, 2 places to the right, and that is the amount of H3O that remains in the solution in moles, but you got to do the concentration, which is that many moles divided by the total volume, or 0.3 molar. And now we can do our pH calculation. All right, 1 sig fig, 1 place to the right. Piece of cake. So these are starting to feel a little bit the same to you. Again, you just sort of kind of work yourself through these problems. Okay, so I'm actually going to stop there again because I don't want to start this problem. So we've got this will now be the end of lecture 4, and you can move right on in to the next lecture 5.